All right, folks. Good to see you all this morning. It looked like everyone had decided, even though it didn't snow, they were taking a snow day anyway. So I was anticipating a lighter crowd, but look at your dedication. Pats on the back all the way around here. Before we get into finishing up our discussion of what makes benzene benzene, and then talking about the actual reactions of benzene, we're going to go from chapter 15 to chapter 16 here. I want to talk to you about Action Center. It occurs to me that a bunch of you don't like my Action Center time that I picked out. I looked at my schedule and I was like, Wednesday afternoons are perfect for me. It's right after class. I still think it's a great time because you could practice the material right after looking over it. It's fresh. And then you have a quiz on Friday, so you have plenty of time to practice things. You all don't like it. And Action Center for Action Center's sake is no good. It's only good if people are actually, there. So, and I think Mr. Cruz, who's not here, was distributing a petition to try and see how many people could come to a Friday Action Center. Before I officially do this, a raise of hands, and I think there's going to be some votes both ways. If you like Action Center where it is right now, Wednesday afternoon from 3 to 4, raise your hand. A couple of us. If you like Action Center Friday, right before class from 1 to 2, raise your hand. Okay. This week and this week only, God help me. We're going to do both. I'll have an Action Center today because I didn't give you enough time to, I don't want to cancel on you last minute here. And Friday, we will have Action Center before class. Probably moving forward, we will move it from Wednesday to Friday in order to get a critical mass of everybody to be able to participate in this. Here's the thing I get worried about with that. Don't let that guide your study habits. If you are studying the material an hour before you're asked to take it on a quiz or an exam, you are going to get rocked. Don't do that. Putting the Action Center right before class, I'm worried sends the message of, hey, let's all learn the material right before class. Don't do that. We will hold Action Center on Fridays before class until I deem it destructive to your learning, and then I will move it back to Wednesday. We understand? Okay. For those of you who like Wednesday afternoons, I apologize. What you can do is we can still meet Wednesday afternoons as a group. I will just not be hosting both of these. It's a large time commitment to set these aside. I like you guys a lot, but I do like a couple other things as well. So this week we'll have what should have been 3 Action Centers, but one got canceled on Monday. So we'll have one today after class. We'll have one Friday before class. You have a quiz on Friday. Okay, good talk. Let's finish up our conversation about what makes things aromatic. We've talked about the general rules of aromaticity. We talked about molecules that have heteroatoms in them. We've talked about molecules that have charges. The last bit here, section 15.6, are polycyclic aromatic compounds. Polycyclic meaning multiple cycles. I've actually already brought up one of these to you, with you, to you, around you, in your presence. This molecule is called what? See if my stupid story stuck. Oh my gosh. This is a touch. What is happening? Is this real? I've been using this for 7 years and never knew. Okay, sorry, that was distracting. New skill unlocked. Why is that helpful? What is the name of this molecule? Naphthalene. Where do you find naphthalene? Mothballs, there we go. All right, so the mothball story stuck, not the structure of naphthalene. This is good to know. We said that naphthalene is aromatic. It's not that naphthalene has a benzene ring with this thing hanging on. All of naphthalene is aromatic. So the way we do this is we just count the electrons around the entirety of the molecule. We do it the same way we've been counting other electrons. Everywhere you see a pi bond is 2 electrons. There's no charges here. So 2, 4, 6, 8, 10 electrons. 10 p electrons. Does 10 fit into 4n plus 2? Math. Let's do it. Let's do it in a different color. Electrons. 4n plus 2 equals 10. I would guess and check it if I were you, or you can solve it. 4 times 1 is 4, plus 2 is 6. 6 is not 10, that's not right. 4 times 2 is 8, plus 2 is 10. 10 is 10, passes Huckel's rule. Or you can solve this, right? 10 minus 2 is 8, 4 goes into 10 2 times, and equals an integer. This is aromatic. So it's cyclical, it is conjugated, and it passes Huckel's rule, right? So aromatic. We see how I did that? I didn't count just this as aromatic. That is a benzene ring, but this doesn't act like benzene. It acts like one or like two benzenes connected together as one entity, one aromatic molecule. My racetrack isn't here. My racetrack is around the entire molecule. That one's probably easier to see than, let's say, this one. These always throw me off because when you put nitrogens in the ring, you got to like interrupt your carbons. And you're like, man, I just learned how to draw a hexagon. Don't put nitrogens in there. Screws it up. Nope, 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 nope. This molecule, in addition to being exceptionally difficult to draw, I see it on your faces, is called purine. Anybody ever heard of purines? It's the other side that we talked about. So we talked about pyrimidines. Pyrimidines cut. Cytosine, uracil, thiamine. Purines are pure as gold. Ag, adenine and guanine. I won't write these out because you don't need to know adenine and guanine for this class. But if you're curious, if you want an easy way to remember your nucleobases, pyrimidines cut, purines pure as gold. I think it's a super easy way to figure that out. Is purine aromatic? Intuitively, yes, I would hope so, right? Because the pyrimidines are, and again, we want our DNA to be super stable. So is this aromatic or not? We got to count up our electrons. Anywhere you see a bond, definitely involves those electrons. So 2 electrons here. How about this lone pair? No, because the nitrogen is already involved in a lone pair. I'm sorry, the nitrogen is already involved in a double bond. So the lone pair is in an sp2 orbital hanging off the end. It is not in the p system. 2, 4, 6, can ignore that. 8. Count the lone pair or don't count the lone pair? Count the lone pair. But count the lone pair, it does 2 things for me here. Number 1, if I count the lone pair, it's in a p orbital, which means this nitrogen is sp2 hybridized. If there's a p orbital here, we are conjugated around the entirety of this molecule. If I count the lone pair, I also get 2, 4, 6, 8, 10 electrons. 8 electrons is anti-aromatic. But if I don't count this lone pair, it's not even anti-aromatic, it's just non-aromatic because this wouldn't be conjugated across that nitrogen. So remember, the trick here is if the lone pair can get involved to make the molecule aromatic, it will do that. Purine is aromatic as well. You see it? Ish. Let's do one more. Spoiler alert, it's aromatic. I want you to tell me how many pi electrons are involved. So bond is here. That is awful. How many pi electrons involved in this molecule? This is, by the way, called indole. Rin, I like the confidence to walk in late and answer a question. You're on the hook. Is 10 pi electrons aromatic or not aromatic or anti-aromatic? It is aromatic, right? 10 pi electrons fits into 4n plus 2. Same thing we saw over here. How do we get to 10 total electrons? 2, 4, 6, 8. Do I count the lone pair? Same story before. Yes, if I count the lone pair, a p orbital is there, and I get to 10 pi electrons. So this molecule would also be aromatic. If it was 8 pi electrons, this molecule would not have a p orbital here, and at least this portion would be non-aromatic because it's not fully conjugated. If it has 8 pi electrons and is cyclic and fully conjugated, then it's anti. Does everybody see the nightmare sort of question that you're gonna, or can everybody envision the sort of question you're gonna see on Friday? Here's a series of molecules, label them like this. Dr. Green's gonna be mean and use examples that are not with things we've seen in class. Want to know how to prepare yourself for said quiz? Do the homework. You should also go to Action Center. I'm hosting so many of them. No, you're not responsible for the net. Well, this one we talked about, right? The other ones, don't worry about them just yet. Both of these show up in biology. Purine or nucleobases. Where do you find indole? What's that? Tryptophan. That's right. You use it in proteins. It is a side chain. Chapter 15 is the appetizer for what is the full meal of chapter 16. I have 5 pages of notes on chapter 15. I have like 16 pages of notes for chapter 16. Want to know why? Chapter 16 is the real deal. Chapter 15 is like, hey, y'all, benzene's a thing. It's pretty cool. Chapter 16 is about the chemistry of benzene. And if I have not freaked you out yet in class, emotionally prepare yourself to be maybe a little bit freaked out. We're going to get into it. We're going to talk about a reaction called electrophilic aromatic substitution. Electrophilic aromatic substitution. I am never, ever going to write that fully out again. What am I going to call it? EAS, it's in the game. We have at least 3 sports video games fans in here. Excellent. Is that still a thing, by the way, EAS? EA Sports. Madden is the one I remember for that. Okay, what I have typically done, none of you have your cameras on. This is embarrassing. Such a camera hog over here. Let's see, I want to make myself big. Not Jayla, me. Make me the, nope, why not? Can I pin myself? This is not that important. But now I have to now I need to know why it's not working. Okay, I'll just be this little, wait, here we go. Pin, now do it. Here we go. That's what you need is more me. You can't see me well enough. I need to be right here in front of you. Usually in this chapter, I put up this diagram. And then this is the point when everyone goes, oh my God, I quit. When's the place where I can get my full refund? We're past that point, so you're trapped. The reason that I show you this diagram is this is a roadmap of all the things we're going to talk about for electrophilic aromatic substitutions. Notice in the middle of this diagram is benzene. And then all the spokes coming off of this are things we can add to benzene. Every one of those reactions is going to behave in a very similar fashion. I don't need you to know these reactions yet, but I want you to be aware of, I'm going to throw at you 5 or 6 different looking reactions that are all very similar to each other. I'm going to show you the mechanism for every single one of them. If you treat these as 6 independent reactions, you are going to have a bad time. Getting self-conscious now. Oops, over here. I want you to think about this as I'm going to learn how to ride a bike. And when I learn how to ride a bike, then I can ride a blue bike or a pink bike. It can have ribbons, it can have other stuff on it, but I'm riding a bike. There is a similar mechanism that each one of these reactions are going to have that'll be very helpful for you, I hope. At the end of this chapter, go back to that diagram and it makes an excellent study guide. It is on the first page of chapter 16 in your book. The book that you have that you read for class, that one. Okay, you have been warned. Before I get into this, I want to bring up the chemistry that you've seen before. Back in the day when life was simple and you had hope for the future, we took things like alkenes. Actually, I've already shown this to you, so you're well aware of what happens. If you take an alkene with an electrophile, you can pick up a proton from that double bond. I'm going to put the positive charge over here. Marky Mark says so. And then in my second step, chlorine that came off of this molecule is going to add to that carbon. We called this an electrophilic addition reaction. This is an electrophile. Maybe not another arrow. This is an electrophile. And so we call this an electrophilic addition. We're going to follow this mechanism kind of similarly, but we're not going to end with an addition. We're going to do a substitution reaction. There's going to be a big reason for that, and it has everything to do with benzene being so stable as an aromatic molecule. So, first reaction. We're going to take benzene. We're going to add bromine to it. And we're going to use some sort of catalyst. I'm going to show you several different catalysts along the way. FeBr3 is a catalyst. What is a catalyst? Speeds up a reaction. How does it do that? Yeah, lowers the activation barrier. Is it consumed in the reaction? No, it's one of the telltale signs it is a catalyst. You see a reactant on the reaction side and that same reactant on the product side. It wasn't consumed in the reaction. It was a helper molecule. It is a catalyst. That's FeBr3. That's the FeBr3 role here. We're going to add a bromine. I'm sorry, we're going to substitute a bromine on benzene. So if you're paying attention to this, there was a hydrogen here. Now there's a bromine over here. What do you think we should call this type of reaction? Substitution, but this particular one, bromination would sound good, right? This is an EAS reaction, and in particular, it's called a bromination. So electrophilic aromatic substitution is the parent class of this. Bromination is the specific reaction that we're running. Aren't you just so curious about how that works? I can tell back there, Danielle wants to know. She's got this like look on her face. She's like, I didn't come here to just like gloss over things. I need to flip over some rocks and look for the bugs. Let's do it. The mechanism of how this works is going to occur in 3 distinct steps. I just got done on a whole chapter telling you about how stable benzene is. What does that mean for benzene's reactivity? If benzene is very stable, is it reactive or not reactive? Not reactive, right? Stable means low energy, not reactive. That's a problem because I'm trying to get benzene to react here. So I need to make benzene motivated to participate in this reaction. That's what iron is going to do for us. It is going to make bromine irresistible to the benzene molecule. When benzene runs into a bromine just by itself, it goes, no thanks, bro, 150 kilojoules per mole, more stable. I don't want to mess with you. But when benzene runs into a bromine that's linked up with iron, it's like, what's up? It's much more reactive. So the first thing we have to do is activate the electrophile. Dr. Green has no game, by the way. The bromine activating looks like this. We take our catalyst. I'll just leave everything in green here. We take our catalyst and we need to pull electron density away from the bromine. Our benzene ring is going to act like a nucleophile. So we need this to be our electrophile, which means we need the halogen to be as electron poor as possible. One of the ways we can get away with that is to remove electron density from one of these halogens. All right, now this is going to look really strange because iron we don't really talk about very often, but iron was neutral and I just drew an arrow towards it. So what does that mean for iron now? It has a negative charge on it, right? It has gained electron density. Bromine was neutral and I drew an arrow away from it. What does that mean for the bromine now? It has a positive charge, right? So there's going to be a plus over here and a minus over there. We can also do our formal charge analysis for bromine. It's not so easy for iron since I'm not drawing everything out here, but for bromine, bromine should have 7 electrons associated with it, be neutral, right? This bromine has 1, 2, 3, 4, all the lone pairs, 5, 6, half the bonds. This bromine wants 7 associated electrons. It has 6 associated electrons, so it has a positive charge. That's the 2 ways you can get through this pretty quick. Either trust your arrows you're drawing and assign charges accordingly, or draw the molecule out and do formal charge analysis. We are talking about the same thing from 2 different angles here. This is our first step, which is to activate the electrophile. The next step is that benzene is going to attack the electrophile. So again, when benzene was floating around solution, it would run into a bromine, not interested, no reactivity here whatsoever. This molecule, though, is very reactive. How do you guys feel about a bromine with a positive charge? Bad. Why don't we like bromine with a positive charge? It is extremely electronegative. It's not stable because it really, really wants electron density. It is one of the more electronegative atoms on the periodic table, and we just gave it a positive charge. That elevates the energy of bromine quite a bit, which means this molecule is now very reactive. And even if the nucleophile is like crappy, which benzene is a very crappy nucleophile, it's more than willing to add electron density to this dire situation. Now, the thing you need to watch out for is when we draw a bromine with a positive charge, the thing most students want to do, don't draw this, is to take a double bond from benzene and attack the bromine with a positive charge. It just feels natural, right? There's a positive charge, draw an arrow towards it. You're about to break the octet rule if you do that, though, right? Because we're going to have to kick something off here that's going to leave us really unstable. So what we're going to do instead is we're going to deal with this positive charge, but we're going to deal with it by the benzene attacking the bromine on the end and breaking that bond onto that bromine. So the bromine with a positive charge ultimately receives the electron density, but through a different mechanism, through a different pathway. I'm going to need this space. If I were you and you probably have more space below, just point down and go the other way around. I'll go up this way. Okay, at this point, we are going to have a benzene where the double bond has gone away. I have added a bromine here. There is still a hydrogen present. I have a double bond there, a double bond there. This molecule is now FeBr4-. It still has a negative charge on the iron. I haven't done anything to help that iron, but we're not going to worry about that part right now. So it's just going to leave. Notice an iron and 4 bromines. How many carbons present? None. This molecule is dead to me. I'm an organic chemist. I don't care about these inorganic things. They are spectators. What am I missing from my organic piece up here? A positive charge. Where, Peyton? The other side. These 2 carbons were sharing a double bond. The double bond went away. The top carbon got a bromine. The bottom carbon got robbed. It had a bond, it lost that bond, and now there's a positive charge here. How do you think benzene feels about this situation? Benzene was floating around on this side aromatic. Is this molecule aromatic? We just asked a lot of benzene. We said, hey, I know you're super stable and like don't want to react with anything, but would you go ahead and attack this bromine? And it was like, okay, fine. And then it did it and was like, what did you just make me do? I have now elevated in energy tremendously. And I want to get back to this more stable state as soon as possible. This is why it's a substitution reaction and not an addition reaction. I don't typically take protons from carbons, but I'm going to take that proton from that carbon because, and I'm going to use generic base. You will sometimes see it used as a bromine that makes HBr. That's kind of dubious to do that sort of withdrawal, but feel free if you want. Any base in the world is going to be happy to take a proton from this molecule. Because if I take this proton from the molecule, trying really hard to not cross over lines here, so I go this way, I reestablish aromaticity. So in my first step, I activated my electrophile. In my second step, benzene attacked. And in my third step, I reestablish aromaticity. This is why it's not an electrophilic addition reaction. It is a substitution reaction because I started over here with a hydrogen. I end, well, you can see it easier here. I started with the hydrogen here. I ended with a bromine there. I substituted the hydrogen for a bromine. I really want to get this double bond back because I really want my aromaticity back. There'd be no reason to do a hydride shift because if I did, I would just switch out one secondary carbocation for another secondary carbocation. But I like where your head's at, Ren, because I've trained you guys well, hopefully, or you've been trained well previously to see this and get deeply uncomfortable when you see a carbon with a positive charge. Not only have I broken aromaticity, but I also have a carbon that lacks an octet. So like two mortal sins here, right? We don't like giving carbons less than 8 electrons. And we really want to keep our molecules aromatic. So why in the world would this molecule ever form? It's a good question. Anybody have an answer for it? Why would this molecule form? Besides the fact that this is reactive, I've told you that. Is there anything making this molecule okay? This one. Lots of resonance. Let's talk about that part of it. I'm going to redraw this. This is where I really wish I had my whole board. Right? Because this needs to be up here while I draw the other thing. So look at your notes as I'm doing this. I'm going to redraw this molecule. There, bromine there. Positive charge there. That positive charge is secondary, but notice that 1, 2 carbons away. Well, sorry, 1, 2, 3 carbons away. There's a 3-carbon unit with a double bond and a positive charge, kind of like a little allyl unit. So I can move that over and draw a resonance structure for that. Oops, not there yet. There. Now my positive charge is here. Can I draw any more resonance structures for this? Yeah, I've got one more double bond, right? So another 3-carbon unit, positive charge here, double bond there. I can move that over. Bashar, you're on fire. Keep going with it. What do I draw? This goes here. Anything here? That one, okay. On top, perfect. And then hydrogen and bromine are still hanging out, right? Which one of these structures represents the carbocation that I formed? It's a trick question. All of them, right? The positive charge isn't here or here. or here, it's at all three of those locations at the same time. The second that benzene attacked that activated bromine, the positive charge spread out across this entire molecule. Because resonance structures aren't like, I'm going to be here, and then I'm going to be here, and then I'm going to be here. It shows multiple pictures of a single structure, of a single molecule. This molecule is called the sigma complex. And if I were you, if I could do this back on the old notes, underneath where we drew this in the mechanism, right, sigma complex. You're going to make one of these every single time you do an EAS reaction. Questions about electrophilic aromatic substitution, bromination addition? Well, it's gone now. I can talk through it. What do you got?
But if we did a hydride shift, that would cause the
A molecule is only going to hydride shift. Sure, but then it has a bromine attached there, right? And the bromine's trying to steal electron density from that position. This doesn't occur. But if the hydrogen hydride shifted, down here, now I have a positive charge over there. And yeah, it's got, well, no, it still lacks an octet, and we have it now attached to a carbon that has a bromine on it. So this is even worse than what it was before.
what happens to that? There would be two bromines, right? Would it attack that?
Well, this just doesn't occur, right? Because there's not, you got to think for the molecule, there's no motivation for it to do that initial thing to then run other reactions. Reactions occur one step at a time. So if there's no path to success there, it's just not going to happen. But I like where your head's at by seeing a carbocation and trying to figure out how to best stabilize it. In this case, the carbocation is best stabilized through lots and lots of resonance. Okay, if you're looking at your notes right now and going, that makes sense, because I think this is rather involved. I'm going to show you a bunch of other reactions that are also going to be equally involved. And I hope by the third or fourth one, you'll go, wait a minute. These are kind of like familiar. Like there's a process that goes into these. I highly recommend writing out the mechanism until it feels familiar. There's a couple of you that have bought into this. One of our classmates carries around a big whiteboard. That's what I did when I was an undergrad. You also feel free to sneak into a classroom and just like write these things out. I started doing it on printer paper at first and then felt like I was wasting like too much paper. So that's why I got into something erasable. Write the mechanism down with no visual aids, erase it. Write the mechanism down with no visual aids, erase it. Do that over and over until the mechanism feels comfortable. Do that now. And the rest of this chapter, the rest of this class feels much more approachable. Mechanisms are scary. They are the hardest thing I'm going to ask you to do. And I'm going to ask you to do it a lot. So practice them now, and I think that it'll be helpful for you. Let me show you some other halogenations. And I won't show you the mechanism for each one of these because I'll show you for one. We'll see. See how we're doing if you need more mechanisms or not. We can take our benzene. I can add on to it Cl2. Now, when I use a chlorine as the molecule that I'm adding to this, I want to match that to my catalyst. You will either see FeCl3. So notice that I've switched out bromine for chlorine here, or you will also commonly see aluminum. This is called iron trichloride or aluminum trichloride. FeCl3 or AlCl3, they do the same thing. But when I'm using chlorine, use chlorinated catalysts. When I'm using bromine, use brominated catalysts. Don't mix and match your halogens. Crazy stuff starts to happen. There's this reaction that you don't need to know about called the Finkelstein reaction, where the halogens switch on each other. And we don't want that to happen. Don't Finkelstein. I'm sure he's a very nice person. This benzene looks a little ornery. What we're going to do is add a chlorine to benzene here, just like we added bromine to benzene. Let's do the mechanism, but you guys show me how. What's the first step? I need to activate chlorine. How do I do that, Mohammed? Just do it. Yeah. I mean, let's stop talking about it and just do it. You like aluminum trichloride? I like it. All right, we got aluminum trichloride. Excellent. Now what? How? Yeah, so chlorine's got some lone pairs. Let's attack the aluminum. Now I have a, oops. Now I have a chlorine, aluminum bond. Again, my aluminum was neutral. It gained electrons. Now it's negatively charged. It means my chlorine is now positively charged. We are drawing a mechanism, so let's draw all our lone pairs out. Takes a little bit more time and it pays huge dividends to know where those lone pairs are. This was step one whenever we activate the electrophile. Cl2, not reactive enough. Benzene is not reactive enough to attack Cl2. This thing is now appealing for benzene to step up and act like a nucleophile. It was the second step. On the next episode of When Benzene Attacks. How do I show that, Bashar? Yep. I'm going to use the double bond from benzene, and I'm sorry I can use any of these double bonds. I'm intentionally grabbing this one because I want to get the chlorine over there, but I can take any of these. That double bond is going to attack that chlorine. That chlorine bond is going to break this way. And we're going to have AlCl4 minus pop off of there. And what is that going to make? Yeah, the sigma complex. Let's just draw out a couple of them. Why not? It's good to practice. Yeah. That can move over. There. I instantly regret leaving color in this image now because I got to do it every single time. And that can move over again. This whole thing is the sigma complex. And the sigma complex is great and all, but the sigma complex is not aromatic. So what's my third step after benzene attacks? We're going to use a base to reestablish aromaticity. So your book will show you sometimes AlCl4. Again, I am more often than not going to just write base in here. The reason I'm doing that is water can take the proton off of this. Anything with any amount of electron density can pull the proton off of this because this molecule is so high in energy and because the product is so stable. And remember, what makes a good acid is a stable conjugate base. This is the acid. This is my conjugate base. You can't ask for a better conjugate base than an aromatic molecule. So this molecule is more than willing to give up that proton to anything that bumps into it, which is why I don't define it almost ever. Doesn't matter where the double bonds are, right? They can move around. Yeah. This molecule, the sigma complex, is acting as an acid here. A base is taking this proton.
Oh, right.
Questions? Ms. Kaufman? No? Many people have the same face. I'm just trying to like spread the love around here. Love it? Love it. Okay, you can put a bromine on and you can put a chlorine on, but I want iodine on this molecule. How do you put iodine on a benzene ring? Can I clear this page? A lot of marks. If I want to put an iodine, which is called iodination, I can use iodine, like the stuff, you probably don't see this used very much anymore. If you're gonna get a shot these days, they probably rub alcohol on you, but back in my day, they'd rub this stinky brown liquid on you, right? Some people still do that. I think in veterinary science, maybe we still do a lot of that. That is iodine. That is just molecular iodine. Eyes, you rub it in people's eyes?
It's otherwise we use chlorhexidine. Chlorhexidine works.
Okay, I don't want to talk about it anymore. Iodine's a really good disinfectant. And I'm sure it's also very painful in one's eyeballs. I've never rubbed iodine in my eyes, but I can just imagine because chlorine and bromine, very painful in your eyes. Like when you put it in the dog's eyes, do they not freak out? Yeah. Wow. I'm just giving you a hard time. To take the here's the deal with iodine. So what we would normally do is you would expect the catalyst we'd use here is iron triodo iron or triodo aluminum, right? FeI3 or AlI3. The problem is, as you go from chlorine to bromine to iodine, we are getting really, really big atoms. Iron and aluminum are also pretty big atoms. So you've got a big atom over here and a big atom over here, and they're trying to make a bond. What do we know about really big bonds? Easy to break, right? You've got a nice tight handshake. If two T-Rexes are shaking hands, they're not letting go. But if you have a long-armed dinosaur, shake hand, can't think of one. It's very easy to remove those bonds, right? Because the electrons are so spread out. Iodine does not make a stable bond to iron or aluminum. So this is the one time we're going to use a different metal and a different halogen. The only time we do this, where you're mixing the thing we're going to add on with a catalyst that doesn't match, and that's just because iodine doesn't make stable bonds to transition metals. At the end of the day, though, you're going to get an you're going to get an iodine on here. I don't know why I keep drawing smirky benzene rings here. And so we're going to put an iodine on here. I am not going to draw this mechanism again for this particular one, but this reaction is called iodination. Sorry, the last one's called chlorination. You might put that on there. The one above this. That one always sounds like coronation, so I'm always like, chlorination. God rest her soul. It was funnier when she was alive. Questions about adding halogens. I've had a couple bombs today, or I was like, said a thing, shouldn't say that thing. Questions about adding halogens to benzene rings. Yeah. CuCl2 is most commonly used. You could get away with some of these other Lewis acids to remove electron density, but this copper makes a tight bond onto the iodine. Really what's going on here is the copper is the thing that's going to receive electron density. We need the copper to be electron poor. Fluorine is the most electronegative stable atom that you can add on there. Fluorine gets complicated. So the Cl2 is just making this copper electron poor so that the iodine gives it electron density. So others are possible. That's the one you'll see most likely, most common. All right, those are all the halogenation reactions. So we can do chlorination, bromination, and iodination. The next one I want to show you is called aromatic nitration. And I think I've just given up on section headings in here, but we're probably in section 16.2. Maybe. This is aromatic nitration. All right, aromatic nitration is a pretty hardcore reaction to run because what we're going to do is mix in HNO3. What is that called? Nitric acid. Nitric acid, strong acid, weak acid. Strong acid. You don't mess around with nitric acid. Want to know an acid that's even stronger than nitric acid? Sulfuric acid. We're going to mix that in there too. That's why this reaction is so hardcore. H2SO4 is sulfuric acid. We are going to protonate HNO3. We're going to protonate a strong acid with an even stronger acid. Lots of rooms for this reaction to explode. We're not going to run this one in our lab. What you're going to, ooh, we want it to explode. I don't like my face. What we're going to get from this is an NO2 group added onto the molecule. I don't want you to draw these like NO2s, especially when you're drawing mechanisms. I want you to show me all the atoms in here because it's really complicated. There are charges present in this NO2, and you can't tell that because it looks nice and neat and packaged as NO2. When you see this molecule, I want you to draw it out in its full glory here. Maybe draw, straight lines. We have a nitrogen with a double bond to an oxygen over here, single bond to an oxygen over here. That gives that nitrogen a positive charge, and this oxygen has a negative charge. NO2 is a complicated substituent. And it's easy to forget about all this when we draw it nice and neat like NO2. Gee whiz, Dr. Green, that reaction looks so cool. I want to know how it works. Don't worry, high-pitched voice student. I will tell you how this comes along here. What's the first step of this reaction? What's that? Come on, dare to be wrong. Activate the electrophile is all I'm looking for here, right? Activate the electrophile. Now, what does that look like? Each one of these things, the activate the electrophile piece is going to look different for each electrophile. Steps 2 and 3 will be the same. So in this first step, as I activate the electrophile, which I'm giving up on color, it's just too much now. I'm going to show you what HNO3 looks like. It's also more complicated than it looks. It is going to take a proton from H2SO4. This is nitric acid, that's sulfuric acid. Now, every time I've done this as an undergraduate, I really wanted to use this O- over here because it's got a minus, right? Why not? It's possible to give this oxygen a positive or give this oxygen a proton, but it doesn't lead to any useful pathway. So it's actually this oxygen that's going to pick up a proton from sulfuric acid. All right, that means that we're going to get HSO4 minus coming off of there. This is a polyprotic acid, by the way. What does that mean, polyprotic? There's multiple protons it can lose. So if you ever look at the acidity of H2SO4, you'll see two numbers. What's it take to get one proton off of it, and what's it take to get the second proton off? We're only ever going to take the first proton here, because this is not a good base. That leads us to a molecule that looks like this. This doesn't look great. I know, reminders, Action Center is about to start. What does this look like? Water, right? If we break this bond, it can be water. If we break this bond, we'll also lose the octet on nitrogen. So what we're going to do is push electron density down from this oxygen to make up for it. Electron density is going to flow down from oxygen and then over here. So we're going to release water, H2O, from this molecule. And we're going to make this feller, which has the most hardcore name ever. It's called the nitronium ion. If you want to know more about the nitronium ion, I invite you to come to class on Friday. But aromatic nitration is not fair game for the quiz on Friday. Everything from quiz 1 up to aromatic nitration is fair game. You want some practice for that? I will see you in Action Center in 10 minutes or before class on Friday. Do your homework too. See you later. Yep.